Good afternoon, everyone. Peter Thomas from Control Specialists. Thanks very much for joining us today. Quite a lot to cover in the hour that we've got available. Hope you're going to find it worth your time. Let's make a start. So basically, this is a webinar on EMC, but specifically aimed for industrial automation systems. I've targeted this specifically to people who would class themselves fundamentally as having a 50-60 hertz background. In other words, electrical engineering, that's the same electricity that we've got going into our houses as we've got going into the an industrial automation system. And there's lots of information about EMC on the web, however, not so much about its application within industrial automation systems. And I put this together having spent half of my time teaching this kind of stuff and the other half of my time on site fixing problems in the areas of PROFIBUS and PROFINET. And that's basically the driver behind all of this. So very brief introduction in terms of who we are. We basically, as I've said, we spend our time supporting industrial systems and the communication networks. I've worked in most industries, primarily the UK, but internationally as well. And we are a PITC, a PI certified training centre, meaning that we give PROFIBUS and PROFINET training courses. I've visited Australia several times to give training courses, so those of you that I've met before, good afternoon to you. Okay, we are planning on giving some other webinars in the next few weeks, and at the end of this, I'm going to be sending each of you a PDF copy of this presentation together with a feedback form that the PAA, the PROFIBUS and PROFINET Association of Australia, have asked me to send to you. We're thinking of doing these webinars shorter than this particular one, but very practical demonstrations, links to a live network, and the opportunities to ask questions. So if it's your kind of thing, you've got a bit of a heads up, and the PAA will send you an email in the normal way. Okay, so basically, let's have a look then at what we're going to do. This is going to be an introduction, and it really is an introduction to the complex world of achieving EMC, electromagnetic compatibility compliance in industrial automation systems. I've purposely removed mathematical formula and try to limit the length of each topic so that we not only can we get it all done within an hour, but also that you've got the opportunity to ask some questions. If you can't think of any questions to ask, if I've bored you to death and you suddenly remember a question to ask, you can always send me an email, and my details are at the end of it later on. Okay, if you're interested in taking this further, we do this as an online training session, which lasts a full day. We've given it several times. We were a little bit skeptical at first at how it would go online, but all the feedback we've had has been good because we've included lots of demonstrations. And there's going to be a bit of a demonstration for you now to give you a flavour. If that's of interest to you, you can always drop us a line. So let's get into the crux of it then. EMC, electromagnetic compatibility. It's basically a term used to define two aspects of the problem, a source and a victim. The source is any item of electronic equipment that's been designed to limit the release of any internally generated EMI into its environment. Probably not our concern. We're going to buy a piece of kit. We're going to assume that it has been designed and is certified accordingly. If that's not the case, then we obviously have a problem. But a source can also be a victim. So we're going to assume that the device has also been designed to be capable of operating within the electromagnetic environment that it's been installed in use. So for example, in PROFINET, could you use normal Cat5e cable that you get from the local store? Sure, you can. Whether it's a good idea in the industrial automation world is another matter. So there's a kind of a case in point. So typical sources then: lightning strikes, high voltage, single phase, three-phase wiring, inverters, switch mode power supplies, contactors switching in and out, obviously transmitting devices, and also PCs, PLCs, operator panels, etc., etc. From a victim point of view, very much the signal transmission cables, PROFIBUS cables, PROFINET and alike. and also the computer equipment that we're installing, again, PCs, PLCs, operator panels, etc. Now, the problem that we've got is that most of the regulations apply to discrete bits of kit. So if you are a company making electronic equipment, your designers will know all about the EMC regulations that they have to adhere to. But when we're putting lots of discrete bits of kit together, even though they may individually be certified, it's not a guarantee that the installation as a whole will therefore have EMC compliance. And we have this term, a fixed installation, and basically because these bits of kit very rarely work in isolation, we have to look at it in slightly different ways. So this definition of a fixed installation then will often, the devices in it will often be manufactured by different companies. They will be installed in wall or floor mounted cubicles, clearly be very different from each other. Some might be instrumentation, there might be transformers, there might be drives, lighting, and so on and so on. They're going to be having cable running between the panels on cable tray. They'll generally or very often be installed in old sites that predate the use of modern day electronics. The bottom line here is that the use of several EMC compliant devices in such a fixed installation is only going to result in an EMC compliant installation if the system as a whole has been designed and installed to proven EMC techniques. How can this be achieved? Well, basically, first of all, you buy equipment that has been designed and tested to relevant standards. So in the UK, in Europe, then we have to get something that's got a CE mark, which is an indication that that has been followed. We ensure that the equipment is installed in line with manufacturers' guidelines, which might seem an obvious thing, but I've lost count of the times where I've gone on site on a PROFIBUS network where there's been problems. My analyzer has told me everything is fine, and I'm clearly on site because it isn't. And I just had a glance and cast my eyes over it from an EMC point of view and just got them to say, check your installer has installed this drive or this bit of kit in line with the manufacturer's guidelines. And invariably they haven't. And when they do, the problem goes away. So you don't need always complex equipment. Being aware of the standards that apply in EMC compliance in an installation, and that is basically where we're going to start looking at. Risk assessing the installation against the standards, because these standards cover a very, very wide range of situations, and your situation may not come under that guide, and therefore what is the point of spending money fixing a problem that you're not likely to get? Ensuring that, excuse me, the electrical designers and installers are aware of the techniques of ensuring the compliance in this fixed installation and also following them. And then, probably more importantly and all, and more probably aimed at the end users here, managing change during the life cycle of a system. If somebody suddenly goes and runs an extra length of cable in an area that wasn't there before, or puts a drive that was there that wasn't there before, the implications of doing that need to be considered to make sure that the EMC compliance that presumably you've got at that stage isn't compromised. So, okay. There's a very important word here. We're not going to spend a lot of time going through standards, don't worry about that, but it's very important because there is a term called normative references. I've cut out a lot of the stuff that was UK European based from this. The bottom line is the standards vary from region to region. You will be conversant about the electrical standards that you guys have to follow, but the theory is clearly international. That doesn't change at all. There is an international standard that is well worth knowing about. It's IEC 61005-2, Electromagnetic Compatibility, Installation and Mitigation Guidelines. And it's one of the few standards that when you look at it, it actually tells you how to do things rather than tell you what you should do and not explaining how to go along. And this document is used in what's called a normative reference. Now, when I first heard of the word normative reference, I hadn't a clue what it meant. But it's basically a list of one or more standards that have to be or must be followed in part or full in order to conform to the standard that's referencing them. So I then throw this back to the electrical guys in the UK. In the UK, all the electrical people over here have to follow this particular guide. We call it the IE regs, installation, commercial or industrial, basically. So there could be people looking at this that are fitting bathrooms and kitchens, as well as people that are about to start wiring a big three-phase drive and things like that. So clearly, it's not necessarily applicable. There's certain sections that aren't applicable to everybody, should I say. When you look in this document, and I'm leading you on here to look in your own guidelines, but from an EMC point of view, this document, which is about 20 mil thick, has only got 6 sides of A4 paper to do with EMC. So there is not a lot there covering what we're going to cover, but the way it kind of gets out of it, it basically references several other standards, and yours will be the same. From an EMC point of view, this document says the requirements of the following standards shall be applied where appropriate. In other words, it's basically saying if you're about to install electrical equipment in an area that you would expect to have EMC issues, i.e. drives, transformers, etc., you need more information than is in this particular book, and you have to look at the following standards. Now, I'm not going to go through all of these, but the interesting point is the bottom one, 61005-2, is a normative reference. And a few years ago, I gave a presentation in Germany about this, and I was introduced saying, oh, Peter's coming along with some new ideas on EMC. And the first thing I said was, this is not new. 61005-2 has been out since 1997. And nothing's changed since. So the amount of people that are aware of this and the potential need to conform to it are few and far between in my experience. PI, the organization, the international organization, PROFIBUS and PROFINET, created a guideline, functional bonding and shielding for PROFIBUS and PROFINET. It goes over a lot of what I'm about to cover in various degrees of depth, but it does have some 6 clear recommendations that you might be interested in having a look at. It is free of charge, and the link is there. So let's have a look at the emissions then. We all possibly think that we live in a 50-60 hertz world, in that we might be putting in single phase or 3-phase cabling, but fundamentally it's 50-60 hertz. What we're going to show you is why this is an issue, in that basically when we're using any of this equipment, the range of frequencies that it can emit can be quite high and certainly well above 50 hertz. The demonstration I'm going to give you is going to specifically point the finger at drives, and that's not because I'm saying don't use drives. Far from it. There's lots of reasons to use drives. What I'm wanting to bring to your attention is, if you don't install these drives knowing some of the things that I'm going to show you, there is a potential problem here, and the drive manufacturers are well aware of this, but the practice isn't always followed. So let's have a look at the issue then. We've got a source, we've got a victim. And there are different ways, different mechanisms in which this electromagnetic interference can travel from one to another. So we have conduction, literally going down some cabling or screening that's common to both bits of kit, maybe a NOT bolt, maybe the bonding, the grounding system, etc. That's one way we can get it. If we've got the equipment close by, relatively close by, I'm talking, let's say, less than a meter or so, in other words, within the distances that we're going to get with cable trays, within a panel, etc., then we can have what's called near field coupling. And there's 2 types. One is caused by changing currents, and that's called inductive coupling, and one is caused by changing voltages, and that's called capacitive coupling. Now, the fact that we are using AC, then by definition we have changing voltages and changing current, so we are going to have some kind of coupling, and these are quite a big deal. You can, in principle, you can already see this is one of the reasons why we would want to have cable segregation, so we keep this to a minimum. But we can also have radiated, which is a combination of inductive and capacitive over a much wider range, and is clearly the principle by which radio transmission works. Now, you might be thinking, well, that's not us, we're not dealing anywhere near that. Well, we're going to show you a couple of things. And since I've been doing this now probably for the last 6 or 7 years, gradually getting through, and I've been helped by some EMC consultants on this, and when they've been telling me certain things, it's not really been, it hasn't been my background, and I'm thinking, what are they talking about? And eventually I've started to look at electrical installations with a very different hat on than I used to. So, a few years ago, I was giving a presentation. There was a guy there from Ghent University in Belgium, and he had this particular slide. They'd done a study, and this kind of tells you the problem, that from an EMC in industrial automation systems, 90% are known to be caused by power electronics. In other words, electronic equipment switching high voltages, high currents very, very quickly. 10% other reasons, whatever that means. From a victim point of view, 90% of the problems are due to bad grounding and references. 10% due to issues with the pieces of kit, etc., etc. But 90% are associated with just the grounding of the equipment. So if we're working in a world where we are installing or using power electronics in an area where we have got a large installation with grounding, etc., well, this is basically targeted directly at you. So what we have to achieve, and certainly in the UK, and I'm assuming in the case of in Australia, it is a legal requirement to, if push came to shove, it is a legal requirement for you to be able to demonstrate good engineering practice during the design and installation of an electrical installation. And basically, you can do this in many ways. It's where installation techniques have been followed to mitigate against the possibility of emissions, coupling, radiation, and immunity. So from an emission point of view, then yes, the designers of the devices can take particular actions to put filters in and shielding, etc., etc. And we followed that by buying their kit and also installing in line with their guidelines. We can take appropriate action in respect of distances, equipotential bonding, selection of cables and shielding to mitigate against the coupling and radiation issues. And then from an immunity point of view, well, again, we take appropriate actions to ensure the equipment is protected against various types. So a number of things that we can do. Now, that's the standards out of the way. You've got a general idea of what's going on. So EMC, yeah, it is a very technical and complex subject. We can start reaming off calculations and formulas until we're blue in the face, but it doesn't do anybody any good. We need to get a fundamental understanding. And what I wanted to do is I want to just spend a little bit of time just basically going over some of the very basic theory to get some terminology, because it is very important. If we don't understand this, and hopefully it'll be a refresher rather than anything else, if we don't understand this, then we can't justify the actions we're going to take in actually mitigating against the EMC. So we're going to do a little bit. We're going to cover the following terminology: resistance and impedance, inductive and capacitive coupling, frequency and wavelength, and differential and common mode currents. And I've chosen these in particular because they are very, very relevant to industrial automation. So we'll whiz through these. Resistance, okay, fairly obvious there. We've got a battery connected to some kind of resistance. We use Ohm's law. That's very easy. If the resistance changes, if it increases, the current goes down. If the resistance falls, the current goes up. And generally, for a given situation, the resistance is going to be constant and will possibly vary in terms of temperature over a period of time. So, okay, that's that. However, we work in resistance is only applicable where the voltage is constant. Well, if we're using AC, the voltage clearly isn't constant, it's continually changing. So we should be using the word impedance. Same kind of formula. If the impedance increases, the current goes down. If the impedance reduces, the current goes up. The biggest difference here, though, is that this load now has a frequency aspect to it. In other words, not only will the resistive component change as a function of temperature, but the impedance aspect of it will change as a function of frequency. So if we are starting to generate frequencies much greater than 50 hertz, we need to take that into account. Now, all of the cabling sizes, I've got nothing new to tell you about how to calculate electrical cable sizes for electrical installations or how to make your system safe. Safety is clearly the prime importance here. I've got nothing new to tell you about it, and there's nothing that will cast doubt on your calculations. However, when we're looking at the bonding infrastructure and we're looking at these cables, in the UK it would be green and yellow, I don't know what it is in Australia, people will call them their earth cables, but very often they're bonding cables. Very often they can be quite chunky cables, and for the reasons I'm going to explain, we can get some high currents flowing down these cables, and they are not fault currents, and I've got some slides to show you later on. So impedance is what we need to be using. We have, in impedance, we have something called inductance. And we basically, yes, it's got a symbol. I'm not talking of a component here, but basically it's the ability or the fact of a system where basically it opposes electromagnetic a changing electromagnetic force. So it basically it creates a back EMF. The faster the current changes, the more opposition there is. It's got a symbol which suggests it's a coil. Well, yes, it would be if you're making an electronic component, but even a straight conductor, a straight length of wire, will have some inductance that at some frequency will be significant. In other words, the current will find it as a high impedance. It'll be way above 50, 60 hertz. That's not a problem, but it starts to come into the equation when we're trying to do EMC issues. Capacitance, similar kind of thing. Basically now where, yes, we can have an electronic component, but we're not interested in that. We will create a capacitor just by having two metal conductors parallel to each other. They're the two plates of the capacitor, and even though they are separated by air and some kind of insulation, then a change in voltage in one will result in a changing voltage in the other. It's called capacitive coupling. We never get any current flowing between the two, but because we're inducing a voltage in the other conductor, that will itself will cause current to flow. So this is how we get this idea of current flowing. Bottom line again, though, is that the further away we can keep the conductors apart, the lower this will be. So what we have to do now is we have to think of a cable now as not just something that's got resistance, but could be represented by this a resistor in series with an inductor. At low frequencies, 50, 60 hertz, etc., this is all taken into account. You can just forget about it, other than the temperature aspect. But as the frequency increases, L will start to dominate. It will become bigger than R, and it will then cause us problems. Here's our formula, V over Z, and if we expand Z, it's the resistance plus the inductive reactance in this particular case. For those of you that remember, XL 2 pi FL. What I'm wanting to show you is F, frequency, forms a part here. If the frequency gets bigger, then basically Z gets bigger, I get smaller. Don't worry, that's about as deep as we're going to get. If we've got two cables next to each other, conductor A and conductor B, each represented by the resistor and the capacitor in series, then the sheer fact that they are close to each other will basically mean that if we've got a changing voltage in A, then this effect of capacitive coupling makes it appear as though we've got several capacitors between the two. And what we will find, if we've got, for example, 240 volts or 440 volts on A, we won't get 240 volts or 440 volts on B, but we will certainly get a sine wave at the same frequency. The magnitude of that will be dependent on a number of things, and one of them is the distance between the two. So clearly we want to keep them apart. The problem that we've got is that conventional cable trays, they'd have to be very, very wide in order to get this down to 0. So we have to live in a world where we will have capacitive coupling. Okay, so, and the main thing is this will increase as the frequency increases. Now, here's a sine wave, and this is very important because it gives you a real good insight. Here's our sine wave whizzing down a cable. We all know that if, no matter really how long this cable was, if we was to put 415 volts at the left-hand side and we had somebody at the far end with a digital voltmeter, they would read 415 volts, give or take, with the volt drop, but generally 415 volts instantly. We don't give the idea, we know it's a sine wave, but who's bothered? But we are, in fact, because one of the things that we're interested in is not necessarily the frequency, it's the wavelength. And if you think about it, if you slow things down, when we first switch our power on at the left-hand side, although to us it's instant, in reality, it has gone up, down, and back up again. There has been a wave. And one of the things I ask people when I'm giving this face-to-face is, does anybody know what the wavelength would be of a 50 hertz signal? Nobody knows. Nobody's come up with it. They might know the period, 20 milliseconds. Nobody knows the wavelength. And the reason they don't know it is they don't need to know it, and it's of no interest to them. But let's just do the calculation. Here it is. It's the speed, V, over the frequency. So when we send an electrical signal down a piece of copper wire, it travels at a percentage of the speed of light. If it's an electromagnetic wave, so if in a vacuum it travels at the speed of light, we're going to basically put a number on there. Let's say it travels at 2/3 of the speed of light, which is typical. Okay, so what's the wavelength then of a 50 hertz signal in a piece of copper wire? Well, if we do the calculation, it's just over 4,000 kilometers. So if you want to tune into a radio station that's broadcasting on the 50 hertz wavelength, then you know what to do now. Just put a 4,000 kilometer aerial above your house, your building, and you'll pick them up fine. So clearly a complete nonsense. Clearly a reason why we guys in the 50, 60 hertz world don't need to be aware of 50 hertz of EMC because of this. But what happens if it was 10 megahertz? Now, I've chosen 10 megahertz particularly, one, because it's in that table, and also two, because they are frequencies that I have measured coming out of certain systems in industrial automation. So let's do the same number crunching. Right, now it's 30 meters. Okay, so what? Well, this next statement was given to me by an EMC consultant that I know in the UK, and this is it. This is the picture that he has when he goes into a site on a consultancy. Any metallic structure in buildings, and by that even cables, whose physical dimensions are greater than 1/6 of the wavelength are referred to as accidental antennas. So if there's a few ifs here, but if we happen to be living in a world where there are currents flowing in the order of 10 megahertz, then anything greater than 1/6 of 30 meters has the potential of being an antenna. And all that basically means antennas radiate, so the problem can get worse. So that's worth focusing your mind now. And one of the things that I'll be using quite often in here is the word frequency of concern, because the amount of effort that we have to put in to fixing problems, or if we haven't got problems, mitigating against potential problems, the amount of effort we need to put in will be based on, well, what is the frequency of concern? And you don't have to go into a lot of calculations or depth. You just need to say, well, what kind of kit are we looking at? So if you're generally looking at drives, well, okay, 10 meg might be a bit high, but it's a nice round number. Let's use that. That it kind of focuses your mind. This is going to have a direct implication on the bonding infrastructure, how much bonding we need to do. Let's move on to currents then. We all know what this is, differential mode current. We might not call it differential mode current, but it's basically where we've got a supply on the left, we've got a load on the right, there's some resistance in the cabling, and the current flows out of the top through the load and back again. It's just normal current to you and me. However, if we place this circuit next to some conductive medium, I've shown it ZE, assuming, let's say, that we're near the ground, the bonding of our site, something different happens. By nature of the fact that we're using a sine wave, an AC supply in the circuit, we actually get capacitive coupling. And as we've seen from before, if we've got a change in voltage in the circuit, it will induce a change in voltage in the other circuit itself. And what will happen now is we're going to get currents flowing that actually are flowing in both cables, or appear to be flowing in both cables in the same direction. Now, the consequence of this is quite significant. When I have more time, I give a demonstration of this. I'm still going to give you a demonstration, but this is a significant issue, and I think most EMC guys would agree that most of the EMC issues that we have in industrial automation are a result of uncontrolled common mode currents. Now, this is quite difficult to get your head around if you are, like me, have been taught the conventional way of currents flowing. Nothing is arcing across. We're not getting any arcing between here. It's simply the fact that there are voltages being induced in the ZE line that result in currents flowing as a result of being in close proximity to this circuit. There are many causes of common mode currents, and a lot of the drive manufacturers will have diagrams trying to instill in this. They know all about it, and they are telling you how to resolve it. Okay, so let's give you a bit of a demonstration then. I've got with me a scope, an oscilloscope, and a spectrum analyzer. Not because I want to think that you've all got to go away and buy a scope and an analyzer. I'm mainly interested here in showing you what the issues actually are. Why we would use a spectrum analyzer rather than a scope, which might be a passing interest, but hopefully this demonstration will instill in you what the issue is when we are using things that switch on and off very quickly. First of all, I'm going to show you a scope, how it shows you a sine wave, a square wave at different frequencies, and the limits of a scope. And then I'm going to connect the same signal to a spectrum analyzer, and we'll show you what's going on there. And then at the end of it, you'll have a better idea of what the actual main issue is. This is the circuit. I've got 3 bits of kit, a waveform generator at the bottom, which basically just allows me to generate different signals. Signals of amplitude, of frequency, and of shape. At the moment, it's set to a sine wave. And what we're going to do is I'm going to let you have a look at this on the spectrum analyzer, on the scope, and then we'll just expand it. And I'm going to add 2 signals to show you, well, what happens if we have a low frequency and a high frequency? What happens there, and how does the spectrum analyzer show itself? So let's basically move on to that. So bear with me a minute while I bring this. There we go. Right, so I'm hoping you can all see my scope here. This is now displaying a sine wave. You wouldn't know this, you'd have to look very closely, but this is currently a 5 megahertz sine wave with 500 millivolt peak to peak. It doesn't really matter, they're just nice round numbers. So let's just make sure that we're all singing from the same hymn sheet. If I make this 2 megahertz, there's less cycles per second. If I make it 10 megahertz, there's more cycles per second. So I'll take it back to 5 megahertz there. If I change the amplitude, now this is more interesting. It's 500 millivolts at the moment. I'm going to change it to 100 millivolts without pressing any buttons on the scope. So here's 100 millivolts. Okay, it's gone smaller. Let's change it to 10 millivolts. Now we've got a problem, because if I want to see this, I'm going to need to zoom in. So one of the issues that a scope clearly has is an inability to display very large values against very small values. We can't get them on the same screen. Okay, so let me just set that back to where we were, to 500 millivolt peak to peak. Okay, and okay, while we're at it, then I can just show you, well, what does a let's just change that to 2 megahertz. If I change that to a square wave, there's a square wave. There's a little bit of a reflection there, but it's a square wave nonetheless, and I can change the frequency of that, and I can change the amplitude. So okay, there we go. What I'm going to do now, though, is let me just change everything back as it was. And I'm now going to show you a spectrum analyzer. And what I'm going to try and do is just get it so it sees both. Now, there you can just about see you can see the scope and you can see the spectrum analyzer there. You'll notice that the biggest difference is that what this scope does is the x-axis, the horizontal axis, is in units of time, whereas in the spectrum analyzer, the x-axis is in units of frequency. And what that's telling me, the resolution is not fantastic, but that the numbers on that peak are currently telling me that this is a 5 megahertz. So it doesn't actually tell me the details of the shape, but it certainly tells me the frequency. If I was to change that, it's 5 megahertz. If I was to change that to 10 megahertz, it's very easy to read. If I was to change it to 15 megahertz, it just moves along. 2 megahertz, and so on and so on. So, okay, now you see the difference between the two. Now, let's show you the first benefit of a spectrum analyzer. I'm going to change the amplitude. It's 500 millivolts peak to peak. Let's change it to 100 millivolts peak to peak. It's gone smaller. It's gone smaller on the spectrum analyzer, but not as much. Let's change it to 10 millivolts peak to peak. Hardly anything on the scope we're still seeing there. I'm going to change it to 1 millivolt peak to peak. And we can still see it. So the reason that we tend to use spectrum analyzers or that kind of thing is that we can basically clearly see the frequencies that we are interested in. Now, let's now go back on there. Right. So what I'm going to do now is I'm going to show you now the effects of making it a square wave. You saw before that, okay, it was a square wave. So what? What I'm interested in is seeing what the spectrum analyzer shows you when we go to a square wave. So we are currently at 2 megahertz, and I'm now going to change it to a square wave. You'll see that on the right, but let's see what the spectrum analyzer makes of it. There's the square wave. There's the sine wave. And if you look at it on here, at the moment, I've scaled that spectrum analyzer so it actually stops at 30 megahertz. But if I just go on to here, just bear with me a minute while I disappear out of the picture. And I will make that stop a wider scale. You can see it goes off into the distance. If I go back on here, there's your sine wave, there's your square wave. So therein lies the issue. This is what a drive, amongst other things, is doing. It uses pulse width modulation on the output of the drive to basically switch on and off something in the order of 600 plus volts on and off. There's your square wave. The rate it does so is round about between 2 and 20 kilohertz, but the actual harmonics that we get generated moving off into the distance can go up into the megahertz. And that's just a function of what they do. That is, we have to live with it. There are many benefits with drives, but the consequences of not installing a drive correctly can leave us with significant issues here. The other one thing I wanted to show you then was, I'm just going to set this back to the same scale on the x-axis. So there's our 2 megahertz. What I'd like to show you now, we'll just go along here. I'm going to introduce another signal into here so that they're mixing as though I've got two signals connected on it. And if we actually look at that now, and I put that on, okay, well, what we can, if we were looking at that in the real world, what we're going to say, well, there's interference. I have no idea what it is. It's clearly not, it's not a brilliant sine wave. Well, we're going to struggle with the scope, but let's have a look at how the spectrum analyzer shows us that. And there he comes into his own. He's clearly showing us we've actually got two frequencies there. And that's exactly what we've got. I've got one at 10 megahertz, albeit at 100 millivolt peak to peak. And I've got one at 2 megahertz at 500 millivolt peak to peak. So that's the demonstration done. What I wanted to show you primarily out of all of this was that when we are getting anything close to a square wave, the physics behind it basically emit very wide range frequencies, much higher than their fundamental frequency. So you may be aware of the issue with harmonics on the input side, but they are based on a fundamental frequency of the supply voltage. So we're going to end up with harmonics maybe up to in the order of kilohertz. I'm talking here on the output side between the inverter and the motor itself, switching in and off very quickly. We are now potentially going to have currents whizzing around at much higher frequencies. So let me just go back to the presentation then. Let's have a look. Okay, so I think you can hopefully see that. Yeah, so we're back there. So okay, so let's now move on. Now that you've seen the crux of the problem, what do we do about it? Well, the bottom line is there are several techniques that can be followed to provide evidence of good EMC practice in an industrial automation system. What do they include? Right, adequate separation between cables of different categories, terminating the shields of all shielded cables at both ends. Now that's very contentious, and I'm going to come back to that shortly. But also to a low impedance bonding network, and I've chosen those words carefully as well. You avoid the use of pigtails, the idea of getting a shield and twisting it together and putting it into a screw terminal. It's often easier said than done, because very often the manufacturers give you a terminal. What are you supposed to do about that? So we'll talk about that shortly. Ensuring that the low impedance bonding of all cubicles, it basically that it's bonded to that. Now, in my experience, I tend to go around now when I'm on site, if I tend to see green and yellow wires bonding the sides of cable, green and yellow being the UK colouring for earthing cables. If I see green and yellow wires doing that, I basically say this is designed to good safety, but it's not necessarily good EMC. Why am I thinking that? I'm not saying that they've got a problem. I'm just basically commenting at a high level. Terminating the shields of all shielded cable on entry and exit to all cubicles, and many more. You may be doing this already. So if that's the case, you can start putting a few tick boxes in terms of these are evidence of good EMC practice. So let's have a look at a few of them. We have the idea of cable categorization, segregation, the idea that an installation is likely to have many different cables in there, some low voltage, some high voltage, some low current, some high current, etc. And basically, the designers try to categorize them so that they can bunch them together but run them separately from other cables. So we might have a simple one of category 1, 2, 3 and 4. So we might have sensitive cables in 1, low voltage in 2, high voltage in 3, and anything from lightning strikes in 4. These recommended distances, when I've looked at them, you can look at different standards and they very rarely quote the same numbers. They're all very, very similar, but they're slightly different. Typically, we are looking at between 100 and 150 mil between these kind of categories. There is a standard 50174-2 that PI have updated their guidelines in accordance with, and that actually allows you to have much smaller distances. but it does assume a number of things. If you're interested in looking at that or wanting to ask questions, just give me a shout. But here we go. If we've got these cables in different categories, then we might have this kind of thing. That's basically it. So if we were doing this in a cable tray, it would be something like this. And if space was short, then we might need to put it in a steel enclosure to achieve the same mitigation against coupling. Okay, right, what about shielding then? Right, the shielding, I'm now talking of the shielding on cables, assuming that the cable's got a shield. So let's assume that it has. And the shield's going to have two purposes. First of all, in network cables, it's to prevent externally generated EMI from getting into those conductors and corrupting the ones and zeros on our data stream. In a variable speed drive, it's the opposite. We want to keep these emissions from the pulse width modulation inside getting outside. The bottom line is the importance is the same in both cases. Now, this is something that we just have to accept. And certainly for some of you, I know you work for companies that work in process industries and in particular hazardous areas. And clearly, I can't tell you don't follow the guidelines for hazardous areas. That clearly takes precedence. What I want to tell you is, though, that if you are in a situation of having to follow guidelines from a safety point of view, you follow them. But be aware that if that is the case, then your shield will not protect you against everything, and that may be a problem, and you may need to take other actions to mitigate against it. So just be clear, safety, hazardous area, etc., that takes priority, but that may conflict with what this is. I'm just talking now about the ideal world and also what we are teaching in the Profibus and Profinet training courses. They must be terminated at both ends. Right, it's not always done because of concerns about creating ground loops. Nowadays, modern day electronics, basically, it's not an issue as such. It might be on the older style, but certainly with Profibus and Profinet and that kind of thing, it's not a problem. In the UK, we call it grounding or earthing the shield. If I ask an electrician what you're going to do with this, they'll say, oh, I'm going to connect it to earth. Well, yes, I understand exactly what he means. I use that term myself in the past. I try to avoid using it now, but I slip. It's an unfortunate terminology because basically earthing and improving the earthing has nothing whatsoever to do with EMC, absolutely zero. And you'll see why that is in a minute. Depending on the frequency of currents flowing in this shield, then the way in which the shielding effect works either to the generation of an opposing magnetic field, or at higher frequencies, it's something called the skin effect. Now, that's something I go into in more detail during the online training. We don't have as much time to go through that here now because I want to give you a general overview. I hope that's not to the detriment of this webinar. But I'm led to believe that the new Dreamliner, the Boeing Dreamliner, has actually got Profinet devices. Well, if those guys have been on the Certified Profinet Engineers course, or the installer course to be correct, they will have been told of the importance to make sure that the shielded cable is grounded at both ends. Well, then in that case, the only way that we can achieve that is to go along and purchase 37,000 foot drum of earth cable, put a weight along and make sure that it's touching the ground at all times. Clearly a complete nonsense. If we don't have EMC in an aircraft, I don't think many people would fly in it. And I don't remember seeing wires hanging from the bottom. So nothing whatsoever to do with the EMC. It's a safety related matter. It's I'm not telling you to change your earthing. You do what you do, but when we're talking about improving, then those improvements will not be to the earth. It will be to do with the bonding, and there is a slight difference. So the principle of dual end, there you can see some cable generating a magnetic field around itself. If we've got a loop that comprises of the shield, its connection at both ends to some kind of bonding infrastructure, then there will be current flowing in, and that current will be 180 degrees, or will generate a magnetic field 180 degrees out of phase with the magnetic field that's causing the problem. And that's one of the mechanisms by which the shield works. If we don't connect at both ends, we can't have current flowing in it, so therefore we can't protect against a magnetic interference. So for those of you that are instilled that we have to do this, we're told we have to do this, well then just be aware the shield can't offer all the protection that you might want it to make. Okay, so what is this bonding infrastructure? Right, well basically the correct terminology is that we should terminate at both ends to a low impedance bonding infrastructure. And the fact that the bonding infrastructure is earthed or grounded is a safety point of view. It's got to be fine, carry on doing it, but we're not particularly interested in that from an EMC point of view. What we're interested in is that the voltage the bonding that we are doing at one end compared to the bonding that we're doing at the other, there should be a relatively low voltage between the two. Now, conventional star earthing, where you might have an earth bar at the bottom of each cubicle and then a very long earth bonding cable to some main earth terminal, that's fine for electrical safety, but that is considered bad for EMC at any frequency. What they are wanting you to do is to move towards a mesh bonded network. Now this thing tends to put the fear of God into people, thinking that, well, we can never get anything to work if we've got to start installing something like this. And that's not the case. What they're basically saying is move towards this, and you can do it in a localized way. You don't need to do this in a site-wide way for particular areas. It's called a mesh common bonded network, and it's described in detail in this document, as well as that 61005-2. The idea is that such a system avoids long lengths of cabling, that cabling has inductance in it, and that would limit the currents to flow. They don't affect the flow of fault currents, but they will affect where these high frequency currents are going. And if you remember, what I said was the flow of current, uncontrolled flow of currents flying around, are the biggest issue. So there's things that we can do in the panel design. Little point in going to the effort of this if the panels themselves don't meet the requirements. So we want them to lay them out with EMC in mind, ensuring a low impedance bond between the cubicle and the network, which doesn't mean a length of cable. We're talking of using straps, braided straps, etc. Minimizing the number of apertures, which is a strange thing. The use of EMC compliant bonding between the sides. This is all in the standards that in the UK we're supposed to follow, and very often we don't follow this because we're not aware of it. Making sure that painted surfaces don't result in high impedance connections, and also 360-degree termination of the shields on entry. So what about existing installations where we go on site? We might be a system integrator. It's not our remit to start making improvements. What we've basically done then, we've covered so far the proven techniques that can be used as evidence of good engineering practice in a new installation. But we might have a system like this, where we've just got old style earthing, perfectly safe. But we can basically apply the same techniques by making improvements to them. And there are various techniques in doing that. But in this case, and this is not my words, these are in the standards, this is considered bad for EMC at all frequencies. It doesn't mean you need to implement a site-wide improvement, but it does mean that you may need to implement local improvements, which are relatively straightforward to do. Variable speed drives then. They're becoming more and more popular as a way of controlling the speed of induction motors, and there are numerous benefits in doing this. The simplest way then to achieve compliance is to follow the manufacturer's guidelines. Well, okay, that's fine. The problem is it's not always done, and when that's the case, it can be quite expensive to go back retrospectively. So what is the problem then? Well, basically the way in which VSDs, variable speed drives, work is they use pulse width modulation. So our 60 hertz supply is rectified internally and smoothed to some voltage, between 600 and 800 volts, depending on the supply voltage. And if we was to put a scope across the terminals of the motor, we would not see a sine wave. What we will see are on-off pulses. Maybe not as neat as square as this, but basically a square wave nonetheless. And it's using pulse width modulation. And the effect of this and the inductance that we have in the cabling in the motor results in a current that is approximately the same as a sine wave. You would certainly see a sine wave there. When we want low current, then we have a small pulse. Higher, we have a wide pulse. So we now know from what we've seen, well, they are going to generate a wide range of emissions, because that's what we get when we get square waves. We're using thyristors or IGBTs, insulated gate bipolar transistors, to switch these either on or off. And as I've said, the earlier demonstration should have shown you the potential issue. We are switching these at an adjustable frequency of between 2 and 16 kilohertz. But that's going to be the fundamental frequency. The range of emissions goes well beyond 16 kilohertz up into the megahertz. Now, despite their obvious advantages, there are a number of disadvantages that we can cater for as long as we are aware of them and follow the guidelines. So we have supply harmonics and filtering. I think my experience is most people are aware of that. With this potential damage to bearings, some people aren't aware of that. And then there's the issue on the motor side, the choice of cable, the general construction, the bonding, the shielding, etc., etc. And we see all sorts of things over here. So this is where I'm getting close to finishing, and this is basically a bit of kit that I used a few years ago. It's basically a 4-channel current monitor, each channel capable of measuring current via a clamp. You can just about make these clamps here where I put coloured circles on. And basically it will read currents up to about 40 kilohertz. So it's still way, way below the frequencies of concern. I did this on a site where I was working at, where I'd been called because it was a PROFIBUS installation. They'd had lots of problems, and my analyzer was telling me everything was fine. And then all of a sudden the network would just die on me and then would come back up again. And I just became aware, well, there's a load of drives around me. I wonder if drives were the issue. So this one was chosen not because it was problematic, simply because it was near me and it was a big one. So we got the electricians to take the cover off, and I connected the 4 probes, as you can see, the clamps, to the following. We've got 2 of them, one around each shield, each Profibus cable. We've got one around this green and yellow, what we would call the earth, the protective earth that's in the supply cable. And I've also got one over this twisted shield. And all as we said to the guys, just switch the thing on. Let's have a look. Now, I show this many, many times. For those of you that when I've been over there, I was there last year and a few years before, you may have seen this. This is just a reminder. I've asked everybody, on the assumption that there was no fault on this drive, which there wasn't, and what would you expect to see in particular on this red probe here, the one going on here? Now, in my experience, I've not heard anybody other than the EMC guys tell me 0, couple of milliamps at best. We'll say 0. Okay, let's have a look what I actually saw. Okay, so remember the red one. This is what I saw. The scale there is in amps. That's an RMS value of about 9 amps. And this was one of many drives, and subsequent visits to this site have shown us that we've got this all over the place. Now, what is the solution there? Well, this is a difficult one because this just gave us an indication that the installation guidelines had not been followed. We clearly, in this particular case, we have got on here a twisting of the shield rather than a 360-degree bonding. There were numerous things, and they're still struggling to try to resolve this. And the situation they're in at the moment is generally things are working, but they have to accept these annoying glitches. It's too big a site. The general idea is, though, is that we believe that we should be able to make relatively low cost improvements to the bonding infrastructure and dramatically reduce the currents flowing in that PE. But at the moment, they are flying everywhere. They have the potential to cause problems. And I've not met anybody that is being aware of that yet. And more importantly, the first thing guys do is they get their normal clip-on ammeter out. It's a complete waste of time. That clip-on ammeter is generally designed to measure 50, 60 hertz current. It might have a frequency range up to a few kilohertz, but it won't be anywhere near the range that we're talking about. So it's just a different world that we live in. So to summarize then, be aware of the standards that apply to the design and installation in your region. Certainly all the techniques I've talked about are international. What you have to adhere to may change. Basically ensure that the relevant people in your organization are sufficiently trained against this, because you get a lot of kickback in it. Does it really matter? Well, let's face it, I've seen plenty of ropey installations and they're fine. It's an insurance policy. You've got to try to show evidence of good engineering practice. Risk assess your particular situation, because you could end up spending money that is of no value and of no benefit because you're not going to come up with the problems. Document it for ongoing purposes and follow good engineering practice. Have a change control procedure in place. Remember, use the term impedance rather than resistance. And knowledge of the frequency of concerns will be very useful. You don't have to do calculations. It's just what kind of emissions are we likely to get from this kind of thing. It's just almost a finger in the air approach. Currents, differential mode or common mode, they're always going to flow on loops, but the problem is they always prefer the low impedance loops. And if we've got high frequencies, some of the cables that we think might be thick, chunky cables are not the obvious places that these currents will flow. They could end up flowing down the shields of our cable by nature of the fact that they have a lower impedance. EMC will be made easier by having common mode currents flow in smaller loops. As the physical dimensions of building infrastructure, the struts in buildings, the cabling approach a sixth of the wavelength of whatever our frequency of concern is, they can, not will, but they can become resonant. And when we talk of an improvement of the bonding infrastructure, we are talking based on, we will never give you guidance until we say, well, what are we talking of here? What frequencies are we likely to be dealing with? If you work in very, very high frequency gigahertz, you're going to have bonding very, very short distances. In our world, we're probably talking much wider than that, but improvements can be made at relatively low cost. But remember, it's improvements to the bonding infrastructure and not the earthing grounding that is going to make the difference. So 3 minutes over an hour, a bit longer. I know it's now 5 o'clock on the east coast of Australia. I am quite happy to answer any questions via the chat. If you want to go, if you've had enough, if I've bored you to death, hopefully that's not the case. My email address is there that you can send me any questions. I will be sending you an email with a PDF copy of this. And also, if you're interested in looking at this again, there will be, it has been recorded and will be made available. Grant, the PAA chairman, has asked me to ask you individually for feedback, and it would be appreciated if you could tell us a couple of things. Yes, certainly from a technical point of view, but also, you know, has this been of use to you? Has it opened your eyes? Did you know it, etc., etc.? Okay, so I shall leave this open now for a couple of minutes. Feel free to ask any questions via chat. It is quite a lot to take in. May actually challenge your fundamental thinking, but basically there we have it.